Gradient boosting is a widely used supervised machine learning model. Let's dive into the mechanics of the model and its training process. The goal of a machine learning model is to predict from known variables an unknown one. The tool that we are going to use for this task is a function. This function is called estimate function. In this estimate function, we put the known variables of a specific observation, and we have as output an estimate of the value of the target variable. The problem is, who is this estimate function? All the training process of gradient boosting is to determine this estimate function. First, gradient boosting defines an estimate function as follows. F of x is the prediction for a given observation with known features x. F sub 0 is called the initial estimate. The initial estimate is a constant. It is the baseline on which we will fit our function. This eta is the learning rate and is also a constant. We will further expand on the role of the learning rate later. Near to eta, we have a sum. The sum of residuals noted h sub m of a specific observation x. Now, we can easily write the mathematical formula into words. But what are the residuals? The residuals work as adjustment variables. Their role is to fit the optimal estimate function. They will be determined iteratively by decision trees. With our initial estimate f sub 0, we create a decision tree. This decision tree has residuals on its leaves. By running the tree, we allocate to each observation a residual. They are then used to update our estimate function. We have now f sub 1. Then, we use our updated estimate function to build again a new decision tree, which will give new residuals used to update the estimate function, and so on until we stop the process and have our final estimate function. In other words, the decision trees are not here to directly predict the target variable, but to polish our final estimate function by giving new residuals. How do we get these new residuals? And how do we know if we are getting closer to the optimal prediction function with these residuals? One tool is used to answer both questions. It's the loss function. The loss function will quantify the gap between what the current estimate function predicts and the actual value of the target variable. The residuals in the decision trees are computed through the minimization of the loss function. By minimizing the loss function at each iteration, we enhance the estimate function's accuracy in predicting the target. By this step, we know that we are getting closer to the optimal estimate function. The last part that we still didn't cover is the learning rate. The learning rate settles how much weight is put on each adjustment offered by the residuals. A learning rate of 0.1, for example, means we only take 10% of each tree suggestion. This approach helps to prevent overfitting, as we don't want to trust any tree too much. Finally, to prevent the algorithm from taking too much time on training, we fix the number of decision trees the model should create. When this number is reached, the system will stop, and we will have our final prediction function that can be used on new observations. In our mathematical formula of the estimate function, this capital M translates the number of iterations made during the training. Now, let's look at an example. We have this simple data set with 5 observations. Each observation has a known variable, occupation, and an unknown target variable, salary. Now, let's train our model. We choose our loss function first. In this example, we choose 1/2 of the mean squared error as loss function. Step 2, we choose the number of iterations. We choose 1 iteration. Step 3, we determine the initial estimate. The initial estimate is our first version of the estimate function, so we call it f sub 0. Several steps are required to determine f sub 0. First, we write the sum of losses. Then, we have to answer to the question, what is the value of the variable prediction when total losses are minimized? For that, we derive the sum of losses with respect to prediction. We get minus the sum of salaries minus prediction. This derivative is set equal to 0. Then, we resolve the equation by isolating prediction on one side of the equality. After isolating prediction and using the values in our dataset, we get prediction equals to 53,750. So our initial estimate f sub 0 is equal to 53,750. Now, we finished step 3. You can notice that this value is the average of the target. So, losses are minimized by the average. We will use this information later in our decision trees. Step 4. With our initial estimate, we calculate the residual for each observation. In our case, the residual of one observation is equal to the salary minus our current estimate function f sub 0. We do the same calculation for each observation and add a new column, residual 0, in the dataset. Step 5. We create a decision tree with the calculated residuals on the leaves. We are not going to detail how we built the tree, but just focus on one thing. On this specific leaf, circled in red, we had several residuals, and we calculated their average to unify them. But why? The reason is, as always, minimizing the sum of losses, as we have done in step 3. We look for the minimum, we derive, we resolve the equation, and finally the result is the average of the residuals. If we have taken a loss function different from the half of mean squared error, the result of the minimization process would be different. Our step number 6 is to run the decision tree, and we get new residuals associated to each observation that we put on a new column called residual 1 in the dataset. Step 5. We update the estimate function. Our updated estimate function is called f sub 1. For example, for t, the model will predict f sub 1 of t is equal to initial estimate plus learning rate multiplied by residual 1 of t. F sub 0 is 53,750. We fix the learning rate at 0.1, and R sub 1 is 46,250. Then, F sub 1 for t is 58,375. We do the same for all observations. As you may remember, we fix the number of iterations at 1, so now f sub 1 is our final estimate function ready to be used on new observations. If the number of iterations is higher, we must do step 4 to 7 again, by calculating residuals r sub 2 using the estimate function f sub 1 and then create a new decision tree, etc. That was the mechanics of gradient boosting. Let's now look at some of its applications.
The gradient boosting model has many applications in real life. Imagine you walk into a bank and ask them for money. How does the bank decide whether they should give you the money or not? They need some models like gradient boosting to predict whether the borrowers will repay it. Or think of a doctor trying to diagnose a patient. If the doctor has information about lifestyle, previous diagnosis, gradient boosting can analyze symptoms and test results to better predict the disease. Or think of a manager who plans a campaign. Will it bring more profits or losses to the company? Before explaining how it works, I need you to remember some key points. First, gradient boosting models work for both regressions and classifications tasks. Second, models use regularization to avoid overfitting. And remember, they love structured data. So think of clean spreadsheets or organized databases. But then, how does it work in real life? I will reuse the cases I just mentioned to illustrate 3 types of gradient boosting models. With the case of the bank, the target is the probability of loan default. And because the target value is continuous, we use regression models. Then, from the probability of loan default, the bank can set interest rate and loan amount in respect to the probability. Then we move to the next case of predicting disease in patients. The target is the disease predictions, and because the target value is discrete, we use classification models. From the predicted disease, the doctor can better make a medical judgment and appropriate action. With the final case of the manager, while the target is the churn decisions and loss, because the target values are both continuous and discrete, we use the hybrid model. From the predicted churn decision and losses, the company can design a better strategy campaign. Okay, so now I will show you how to build your own gradient boosting model in Python. First, you need to import these packages. Then you can create or import a dataset from a library. In this case, I create a dataset from the example at the beginning of the video. We set this value to none because we don't know the salary of Marius. This dataset is in a form of a dictionary, so we need to convert it to a data frame. Then, in the next step, we will encode the categorical feature. This label encoder function will convert text values into numeric values, and this fit transform function will identify unique categorical text values and map these values with numeric ones. Then in step 4, we split the dataset into training and testing data. The training data is the current available data, which is used to train the model. The testing data is used to predict. Then in step 5, we train the model with the training data. The fit function will make the model learns the relationship between salary and activity encoded. Then in step 6, we will print out the prediction of the model. The log function here is to locate the row where name is Marius, and the output should be like this. Thank you for watching the video. I hope now you can understand what is gradient boosting models and you can build a model on your own.